All right, hi. My name is Boling. I'm a graduate student from the University of Washington. In this project, I'm working with Golnaz, Patrick, Professor Brian Boots, and Professor Joshua Smith. In this paper, we explore the novel idea of competitive HRI human-robot interaction. As the first step toward this idea, we make a robot companion that could make exercise fun and effective. In this talk, we'll first discuss the significance of competitive interaction and justify why we believe that it deserves increased attention in the robotics community. We've created a robotic system for competitive HRI research. We use a multi-agent reinforcement learning method to train our robot to play a competitive fencing game with multiple gameplay styles. And finally, we perform 2 user studies with actual human subjects to evaluate the system effectiveness, user acceptance, and more. So, why do we even care about competitive interactions? Indeed, there have been a lot of research on human-robot cooperation, yet not too much on competition. But when we take a closer look at competition from a psychological perspective, we'll find that they can also be beneficial. Psychologists have found that in an educational mathematics video game, competitive players have significantly higher performance and demonstrated higher problem-solving efficiency compared to individual and cooperative players. Moreover, competitive players also experience a higher level of enjoyment with an increased tendency to engage in game. And similar effects has also been found in physical exercises. In tri-mile running, cycling, and the plank exercise, the introduction of competitions significantly motivates human participants and resulted in improved performance. Therefore, if we avoid unhealthy competitions that narrowly and overly focus on winning, we imagine that a robot competitor could be motivated and could potentially inspire our improvement in a given task. On the other hand, creating a robot that can physically compete with humans is technically challenging. The robot needs to constantly reason about the human's intent and strategically control its high degree of freedom body to counteract the opponent's adversarial behavior while maximizing its own reward. With these technical challenges in mind, we've designed a zero-sum attack and defense game as the evaluation environment for our system and the user studies. We call it the fencing game. Each fencing game lasts for 20 seconds. The antagonist agent on the right will get 1 point by placing his sword within the orange spherical area located between the agents, and let's call it the target area. However, the antagonist will receive negative 10 points of penalty if his sword is placed within the target area and make contact with the protagonist's sword simultaneously. Meanwhile, the goal for the protagonist agent on the left is to minimize the antagonist's score by giving him this penalty. Additionally, the antagonist will get 10 points of reward if the protagonist's sword is placed within the target area, passively waiting for the antagonist to attack for more than 2 seconds. This will encourage the robot to play the game more proactively instead of just camping around the target area. Given this research problem, now let's briefly talk about how do we create a robot competitor with a PR2 robot. To create a robot policy that can play the fencing game sufficiently well, we formulate the fencing game as a multi-agent Markov game problem and solve it with a 2-phase multi-agent PPO algorithm. The first phase of training can be seen as a pre-training process, with reward shaping and an iterative training scheme that allows each agent to learn the best response against the most recent opponents. Both agents were able to learn to move and understand the game rules very quickly. However, this kind of best response updates in multi-agent systems are known to be unstable because all agents are rapidly changing, and they could chase each other around a low quality equilibrium and never converge. Therefore, we use the second phase of training to create a more sophisticated policy with different rewards and sampling strategy. The agents are rewarded solely with the game score, which encourage better exploration in their parameter space. In each iteration of training, one agent will play against a random version of the opponents from the history, which diversifies the training samples. The new reward and sampling strategy allowed the agents to learn more complex behavior and improve the convergence property. To make the learn policy work well in both simulation and real-world setting, we choose to control our PR2 robot with a Jacobian transpose and a vector controller. And we perform system identification to tune the parameter for both the controller and the simulation model, such that the end effector dynamic of the simulated robot and the real robot are similar. For experiments, we performed 2 user studies. The first studies evaluate the system's effectiveness from 3 perspectives. First, we monitor users' heart rates change in all games. Second, we assess to users' subjective opinion toward our system with a modified technology acceptance model. And finally, we study the human learning effect in the game. The second user study compare an RL train policy with a strong heuristic baseline policy in a long sequence of gameplays. Before the experiment, we recorded the average heart rate for each subject when they are walking for 3 minutes as a baseline value. We found that subjects' gaming heart rates in more than 92% of the games were higher than walking baseline heart rates. And the heart rates in 1/3 of these games are actually significantly higher than the baseline. So we're talking about around 20% to even 58% higher, which is a little surprising because given the amount of body maneuver required for the game is not that much higher than walking. So to try to explain this, we try to look into the subjective response and finally find that the increase of heart rates also corresponds to or correlated to cognitive effort and some noticeable emotional reaction that were triggered by the game, such as frustration, motivation, and intimidation. And we are glad to see that human subjects are very accepting of a competitive robot exercise companion. More than 87% of the subjects agree that the competitive games were entertaining, and more than 81% of them think a competitive robot exercise companion will be desirable in the future. And around 69% of them agree that a competitive robot could improve the quality of their physical exercise. The second user study compared an RL train policy with a carefully designed heuristic-based policy. Action noise was added to the heuristic policy to create randomness in the robot's behavior. Despite some subjects thought the heuristic policy had faster reaction, the RL train policy was actually slightly better in game score performance. We also found that an RL train policy makes it significantly harder for subjects to learn to make improvement over time. And the subject considered the RL policy to be more intelligent because of its defensive and diverse behavior. So in conclusion, by using a multi-agent RL method, we've created a robot that can sufficiently fight a human in a fencing game. And at the end, I want to emphasize that we are excited about our competitive HRI research, and we hope you do too. Because from the HRI perspective, it is a relatively unexplored area with many open questions waiting to be answered. And from a human control perspective, it is not easy to create a robot with body agility that is comparable to that of humans. So as our next step, we're trying to extend our methods for full body control competitive tasks. So stay tuned, and thank you for your attention. I'm happy to take your questions.
Boling, thank you so much. Great presentation, very cool work. I think we should have a time, for 1 or 2 quick questions. And maybe we can start from the questions from the in-person audience. For that, I think I will need the help from Alexandra or somebody who's in person there. And the catch here is that I don't think we are able to hear the in-person audience, it seems.
Test 1, 2, 3. Hello.
I think you can perhaps type on.
Maybe as the in-person audience are thinking of questions, I can ask a question.
Right.
So it seems like this fencing game is quite an interesting game. I was curious if there are specific properties of this game which make it favorable to use in this multiplayer RL framework, and how did you sort of figure out that fencing is the game that you want to sort of have for this human robot competition?
Yeah, definitely. So first of all, the fencing game is actually a very challenging game, especially for learning. Because if you think about the antagonist task, the antagonist needs to reach out and place his swords within the target area. But at the same time, this scoring behavior also corresponds to potential high risk, because the protagonist will try to catch the attack and give penalty. So this actually makes it both cognitive demanding and physical demanding. And also, one of the reasons why we choose to use this fencing game is because it's actually very fun. We have human subjects in our lab, and really exciting about the game, and playing nonstop. So yeah, and also, of course, the design of the game. Actually, we put a lot of thought on how to make actual human robot competitive interactions, kind of embeds the difficulty into this game. We're talking about how to strategically maneuver their body to actually gain more scores, and give penalty, something like that. So the idea is that basically the robot needs to learn to how to counteract the adversarial behavior from, for example, a human or other intelligent agents.
Thank you, Boling.
So, Boling, there are several questions. I think we have just 1 minute left, so I will ask you just to give quick replies. I will try to sample a couple of questions. The first one is about how many participants were involved in the experiments. And maybe together with that, there is a question from Panag about what is the speed of the arm moving. So again, how many participants and what is the average speed of the arm?
Mm-hmm. Yeah. So for the first user study, we have 16 participants, and for the second user study, we have 10 participants. And for the average speed, I don't have an actual number on top of my head, but basically what we play on the video, like what you see on the slide, are the actual speeds of the robots and the human movements. And feel free to scan the QR code to see more video game examples. So.
Okay, thank you so much. In the interest of time, we have to stop here, but feel free to follow up on the feed loop chat if you want to reply to the other questions. And I will, thanks, Boling. I will pass it back to Laurel for introducing the next presentation.